We're going to use mathematical induction to prove that the sum from r equals 1 to n of r squared, so that's going to be 1 squared plus 2 squared plus 3 squared and so on up to n squared, is n over 6, n plus 1, 2n plus 1 for all n greater than or equal to 1. So let's just get a pen of the right colour. So what I'm going to do to start with is just look at the target expression that I should get at the end of the inductive step. So let's just replace the n with k plus 1. So we should have k plus 1 over 6. Then k plus 1 would be k plus 2. And then we'd have 2k plus 1, which will be 2k plus 3. So that's my target expression at the end of the inductive step, and I'm just going to keep that over there for a second. Okay, so we consider the n equals 1 case first, and then the left-hand side just becomes 1 squared, which is 1. And the right-hand side becomes 1 over 6, 1 plus 1, 2 plus 1, which is 1/6 multiplied by 2 times 3, which is 6, which is 1. So we can say that it's true for n equals 1. So we've proved our initial case. Now we move to the inductive step. So we'll let n equal k, and then that means that the sum from r equals 1 to k of r squared would be k over 6, k plus 1, 2k plus 1. Now what we're going to do is add the next term to each side. So what we have is the sum of r equals 1 to k of r squared, add k plus 1 squared, so that's the next term, is equal to k over 6, k plus 1, 2k plus 1, plus k plus 1 squared. The whole point is, if this one is true, then the very next line must also be true, because what have we done? We've just added the same thing to both sides, and then what we've got to do is try and make this look like that. Okay, so this side just becomes r equals 1 to k plus 1 of r squared. Clearly that's just adding the next term in there. So what have we got here? Well, let's take out a common k plus 1. Let's also take out the 6 on the bottom. What do we have left? So I've taken out k plus 1 and 6 from here, so I've got k and 2k plus 1. Now if I took out k plus 1 from here, I've got the k plus 1, but since I've got the 6 on the bottom, I have to make that 6k plus 1. Just think about re-expanding that bracket and multiplying this k plus 1 over 6 by the 6k plus 1 would give me k plus 1 squared back, so that's absolutely fine. So I've got k plus 1 over 6, and then expanding out in this bracket gives me 2k squared plus k plus 6k plus 6. So that's k plus 1 over 6, and then we've got to factorize here. So I've got 2k and k, so this would be 7k in the middle, wouldn't it? So how am I going to produce 7k in the middle? So if I put 3 here and 2 here, and they're all pluses, that would do the trick. I get 2k squared plus 3k plus 4k plus 6, so that gives me that, which is k plus 1 over 6. And then I've got k plus 2, 2k plus 3, which is my target up there. And as a final step here, I would say k plus 1 over 6, k plus 1 plus 1, and 2k plus 1 plus 1. And then that makes it absolutely clear that we've replaced k with k plus 1 in this expression here. And so all we need then is a closing statement. I'm not going to write down the closing statement. It's, we know it's true for n equals 1, and if it's true for n equals k, then it's true for n equals k plus 1. So it's true for all values of n greater than or equal to 1 by the principle of mathematical induction. It's just a gobbet that you need to sort of write down at the end of these sort of proofs.